Hello everybody and welcome to Climate Change Calculated Part 3. So in Part 1 we saw that the CO2 concentration of the atmosphere has risen from an already high level of 208 ppm in pre-industrial times to currently 410 ppm due to the use of fossil energy and rising. In part 2, we saw that the current CO2 concentration leads to a global temperature rise of about 1 degree Celsius in 40 years. And in the following, I calculate that the current CO2 concentration causes the sea level to rise by about 8 millimeters per year. And I show the sensitivity of the global supply chain to this ocean rise, and calculate that if the South Pole or Antarctica completely melts, then the sea level will rise about 67 meters. So that's quite a lot. So if you're interested, stay tuned. So the question I want to answer today is, what sea level rise can we expect? So the sea level rise is caused by the heat expansion of seawater and the meltwater of the ice on Earth. For our calculation, for the sake of simplicity, we focus on the biggest pieces, the meltwater of Greenland and the Antarctic. We must therefore keep in mind that the actual sea level increase might be even higher. So we can again take the radiative forcing of about 2 watts per square meter for the calculation, to calculate the melting water. And for that we need the latent heat of ice. And the latent heat is basically the energy we need to melt a certain amount of water. And we can find data to it again here in this Wikipedia page about properties of water. And there we will find that for melting of 1 kilogram of ice, we need the energy of 333 kilojoule. So we have this latent heat of 333 kilojoule per kilogram. Yeah, and we know that the energy in joule is identical to watt seconds. So now we can take this latent heat, take the units, and obtain a formula for the amount of meltwater that we get for a certain energy. So here we see our latent heat is watt seconds divided by kilogram, and now we can bring kilogram on the other side and also seconds. So then we have kilogram per second equals watt per divided by CS, right? This is our latent heat. So now we have a formula here which gives us the amount of melting water per second given the power in watts. And we already have the power in watts. It's the 2 watts per square meters. So we know if we now take this power, 2 watts, for each square meter, then we can now calculate the meltwater. So this formula calculates the meltwater in kilogram, which flows in 1 second with a power in watt, assuming that the surface is about already 0 degrees Celsius, so that we don't need to have extra energy for warming up the ice. So again, this assumption is okay because the energy we need to warm up the ice is a fraction of what we need to melt the ice. So again, we can focus on the biggest part here. So since we have the energy per unit area from the radiative forcing, so the square meters, we need the area of the considered ice. So the total area of the ice shield. So here I took the German Wikipedia page because this is where I found the numbers that I'm using here. And here you can find the largest areas are Antarctica with 14 million square kilometers. Then it's Greenland with 1.7 million square meters. And if we take those two together, we get to 15.7 square kilometers, or in square meters it's 10 to the 12th square meters. So this gives us the incident power on the ice, on the surface of the ice, by the radiative forcing, meaning the power that we get, the additional power that we get from the CO2 increase. Right. So simply we take the area, multiply it by this power. So then we have 15.7 times 10 to the 12 square meters times 2 watts per square meters. So the square meter cancels. And then we have the 31.4 times 10 to the 12 watt. Right. So this is our result. This is the total power that is now applied to Greenland and Antarctica. So now we can insert this power into our formula that we just derived, and we get the kilogram per second. So here we just need to plug in the watts, 31 times 10 to the 12 watts, and divided by the CS, 333 kilowatt second divided by kilogram. And then we get this number, kilograms per second, or calculated 94.15 kilograms per second times 10 to the 6th, right? So 94 million kilogram each second. So that's sounds a lot already. 94 million kilograms. It's basically 94 million liters each second. But the oceans are large, so it's kind of hard to say or to guess how much they rise because of this meltwater. And also it's per second, so this is kind of hard to imagine. So let's try to get the ocean level rise per year. So for that we need to convert this kilogram per second into kilogram per year. And for that we just need to multiply this number by the number of seconds per year. So we have 60 seconds times 60 minutes times 24 hours times 365 days per year. Right? And when we plug this into this formula, we get 2.9 times 10 to the 15th kilogram per year. So this is actually even more difficult to imagine. 10 to the 15th is a really large number, and that also shows the advantage of having this exponential notation. In this way we can easily handle really large numbers. So good for computing. So then we can compute or convert this result into a volume, right? Because we need the volume to get a sea level rise. For that we need the density of water. We know that 1 kilogram is 1 liter and 1 liter is 1 cubic decimeter. So we can write it as 1 cubic decimeter is 10 to the minus 3 cubic meter, right? So that means 1 kilogram equals 10 to the minus 3 cubic meter. So we can just replace the kilogram by 10 to the minus 3 cubic meter here in our formula. So again, we take this formula. Here we have 2.9 times 10 to the 15 kilogram per year. And for each kilogram we have 10 to the minus 3 cubic meter here. And we multiply it, then we get 2.96 to the 10 to the 12th cubic meter per year. So now we have a volume of meltwater for each year. So to get a sea level rise, we just need to take this volume and divide it by the area of the oceans, right? Because area times height is volume. So for the corresponding sea level rise, we now have to divide this volume by the area of the oceans. So what's the area of the oceans? Again, we look at Wikipedia, surface of the Earth. So again, I took the German Wikipedia site because it has the numbers I was looking for. Here we have the surface area of 510 million square kilometers. and 75% of it are covered by oceans. And that means we have the area of the oceans as 362 times 10 to the 12th square meters. So this is now our desired surface area, again with the right unit in square meters. So now we can plug it into our formula. So we have our volume here in cubic meters, and we divide by the area of the oceans. So again, this shows the advantage of this exponential notations. We can easily represent immensely large numbers. So here those large numbers cancel to a good part, 10 to the 12 and 10 to the 12, they cancel here. So what's left is then 0.0082 meters per year, or 8.2 millimeters per year. So this is now a more manageable number, which is easily imagined. It's about this much per year. So it's a little bit less than 1 centimeter, or um, um, about a third of an inch. Right. So now we have something that we can more easily imagine. We can, so we get this increase of 8 millimeters per year out of our computation. And of course, we have to double check it to see if it's plausible. And we do that by comparison with two sources. One is this Wikipedia page on sea level rise. Again, the German one, because that's where I got the numbers. And here I have this open data web page about the sea level rise. And here I found this citation. Between 1901 and 2010, the sea level rose by 1.7 millimeters per year. From 1993 to 2010, the average was 3.2 millimeters per year. For the year 2018, the record of 3.7 millimeters per year was measured. So the speed of the sea level rise has doubled in the last 25 years or so. And it shows that actually our rough estimate is actually on the same order. And also we need to take into account that the CO2 levels continuously rising fast. Right? So we took the current CO2 level here, not the one from 1901 or from 2010, but from 2019. So we would expect also larger numbers here. So, but we still have to keep in mind it's a rough estimate, so we can be off by a factor of 2 or so. But still, within that range, it seems we have a good estimate. And that also leads us to the conclusion that it's plausible that the rise in the sea level is caused by the increase in the CO2 concentration, which in turn is caused by humanity burning fossil fuels. Right? So now, using physics, we see cause and result. We see that our burning of fossil fuels is causing the sea level rise. This is what we now conclude from our calculation. So maybe this 8 millimeters per year doesn't sound so much, but it actually accumulates, and it also leads to more frequent flooding of low-lying areas on the world, for instance, Thailand. And I found this interesting case. There was a flooding in Thailand in 2011, and it's described here in this Wikipedia page. So we can open it. You can see big parts of Bangkok in Thailand were flooded by the oceans for several months because basically because this is an event which becomes more frequent with the rising sea levels. And the consequence is actually quite interesting. So Bangkok is actually a center where computer hard disks are produced on a large scale. So a big portion of the world's supply of hard disks for computers comes from Thailand and from Bangkok. Right? And the consequence was, as a result, most hard drive prices almost doubled globally, which took approximately 2 years to recover. Right? So this shows that this regional flooding event has global consequences in the global supply chain. So because we have specialized producers and suppliers, that means a catastrophe in some narrow region might affect the entire global supply chain and affects computer users all over the world. So I remember that actually after these floods, for 1 or 2 years, it was actually difficult to buy computers with larger hard drives because they were scarce, right? Because few of them were manufactured. And it took about 2 years to recover. And this shows the sensitivity. So that also shows if you have more of those events, then those effects on the global supply chain will increase. Yeah, and then how does it continue? Where might it go? So the next question is, what is the sea level rise due to the melting of the South Pole or Antarctica? So how much will the sea level rise only by the melting of the South Pole, which is the largest piece on Earth? Right? It's on land, so the melting of the ice on Antarctica is actually leading to an increase in the sea levels, unlike the North Pole, which is mostly swimming ice. So when it swims and it melts, it basically doesn't change the sea level, but the South Pole is on land, so melting there really affects the sea level. So for this we need the volume of ice of the South Pole converted into the volume of water and divided by the area of the oceans to get the resulting sea level rise. So basically the same approach that we just took for the meltwater. So again, here I have the German Wikipedia link in which I found the data. So here it's stated the ice volume is estimated at 26.37 million cubic kilometers, and this is actually the most accurate number I found. Often you find rough estimates like around 30 million cubic kilometers. So then we need to take into account that ice has a larger volume than the molten water. So we can look at the density for it. So the density of ice is 0.918 grams per cubic centimeter, which is the densest ice. And this density is lower than that of water, which is 1 gram per cubic centimeter. So we have this factor of 0.91 between ice and water. So we can now just take this factor here and multiply it with our 26 million cubic kilometers to get the cubic kilometers of water. And then we get 24 million cubic kilometers of water. Again, we divide it by the area of the oceans and we get the resulting sea level rise. So here the area of the water from Antarctica, and this is the area of the oceans, all the oceans. Here I have the unit of kilometers, so then we get the result also in kilometers. It's 0.0668 kilometers or 66.8 meters, right? So this is actually quite significant. So if all of Antarctica melts, that's a lot of sea level rise. So we don't want to see that. So this 66.8 meters is roughly 220 feet, right? So a lot. But the good thing is it's not quite clear yet how long it will take. So according to our computation, we have 1 centimeter per year, roughly, but we also saw we have the increase in CO2 levels, so this radiative forcing is quickly accelerating. And also it is found that in the ice there are more and more cracks and breaking off of ice shields, and then there's water below the ice shields, which increases the surface and hence increases the melting, right? So here we might have significantly increase of the melting surface, which accelerates the melting. So we can make a pretty safe guess that the increase will be faster than the 1 centimeter that we computed. So then it might be a matter of a few hundred years until Antarctica is molten. We don't really know. It's ongoing research, but the risk becomes clear, right? We are really at the risk of melting Antarctica, and we don't really know how long it takes. So it all depends on our future CO2 emissions, right? If we just continue as we do, we have a rapid rise in CO2 emissions, and that will lead to a rapid rise in sea levels and accordingly faster melting of Antarctica. Yeah, so it's kind of like a game of Russian roulette. Do we continue as we do and risk it, or do we take safety measures? Yeah, and to show the risk a little bit more clearly, the risk of sea level rise, we can take a look at so-called flood maps. So these flood maps are used to see how safe shorelines are, lower lying areas. So I took this flood map here, and this goes up to 60 meters. So I put in 60 meters here to see where the new coastlines are when the sea level rises by the 60 meters. So it's kind of a nice tool. We can actually do a glimpse into the distant future and see how the new shorelines look like. So, and when we do that, we see, for instance, that major parts of the US East Coast completely sink into the ocean, including Boston, New York, and Washington. So this is what you can see here. So here you can see the new coastline, and you can see here you have New Jersey, Pennsylvania, basically the entire East Coast up to the Appalachian Mountains is then part of the ocean. Right? So here New York disappears, Boston disappears. Where you have Boston, here's Providence, Boston is up here. Right? So basically the entire East Coast is disappearing. So that's not good. We don't want that. Yeah, so conclusion here is that the risk of doing nothing becomes clear. We could lose a lot. It can be very expensive. When the South Pole melts, the sea level rises by about 70 meters. And here we can also think about what might happen, for instance, to Asia. Many parts of China and the rest of Asia is in low-lying areas. For instance, Shanghai would be completely disappearing too. Or Hong Kong. So it's flooding all the lower regions in the world, including all coastal metropolitan areas. That's bad, very expensive. So from part 1 we know, in order not to further increase only the current CO2 concentration of the atmosphere, we would have to reduce global CO2 emissions by 80%. So by this reduction by 80%, I mean, we just could be staying at 410 parts per million. This is already a high level. So 80% would not allow us to reduce this level. So 80% is kind of like the least we can do, or we should do, to avoid further acceleration of climate warmth increase. Yeah, so that's actually quite tough. CO2 emissions by 80%. Currently, we don't even manage to do a decrease. Actually, the CO2 level, the CO2 emissions are actually still increasing and not decreasing, let alone by 80%. Yeah, so what can we do? Well, basically, fossil CO2 is in principle a problem of air pollution, right? It's actually not that difficult. We solved air pollution problems before. For instance, in the 1980s with the catalytic converter and unleaded gasoline, which successfully improved the air in big cities and also reduced dying forests. Right? It worked. The catalytic converter worked. In the beginning also there was a lot of opposition to it, but then it actually worked. Then in the 1990s, we had the ozone hole, and there the worldwide ban on CFCs as used in coolants or as propellants and their replacement indeed reduced the hole in the ozone layer, right? So this just banning CFCs was sufficient to solve this problem of the ozone hole. So this is actually an example where a worldwide ban worked and where actually we managed to have a worldwide ban, right? All the countries worked together in this worldwide ban on CFCs. So I'm wondering why we are not just doing the same with fossil fuel, right? It's just another CFC, sort of. So we now must come to a worldwide ban on fossil energy. And this can be done, but it can only be achieved politically, right? Like for the CFCs, there needs to be a political cooperation, and there needs to be rules and regulations for the ban and for the replacement. And there are actually plenty of technical substitutes for fossil fuel, right? We have plenty of renewable energy, which we just need to use and expand. And even today, renewable energy is already cheaper than fossil fuels. We just need to stop subsidizing fossil fuels and instead subsidize renewable energy to solve this problem. Yeah, more about these technical substitutes and technical substitutions in the next video. Okay, so hope to see you in the next video about the technical solution, which will hopefully be more upbeat. Until next time, bye-bye.